I'm never gonna need this. A common refrain heard in and around math classes everywhere. You've said it probably, I know I've said it, but the problem isn't the math, it's how they're teaching it. The math is actually useful, they just don't show you where it's useful. In a blog post, I brought up this problem. If you haven't read that yet, byronbuilds.com/blog. Pause the video here, go read it, see if you can solve this problem. It uses basic trig, but it's helpful. I'm a carpenter, I use this math every day. In the video, I'm gonna show you how to solve this, and just think outside the box, use the math they're teaching you, but in a way that's actually productive, actually helpful, and doesn't end with a light at the end of the tunnel, and a train.
All right, so here's the problem as it stands. This is actual real world scenario. I actually had to frame this. I was not given a radius for the back curved wall of this shower, but it had to be, the circle had to be tangent, so right angle radius to this wall and a right angle radius to this wall. Now this isn't to scale, and even if it was, there's no way to scale off this drawing where that radius would be, because you don't know where the center is. You don't know on this wall or on this wall where tangent to the edge of the circle is. You could best guess, cross some lines, measure, check, and go back and forth, but you'll always be fighting something. So there is a way to math this out. This was the information that I was given, a physical measurement on site, the length of that wall, and the shower started 24 inches down that wall. We have a right angle on this side and a 135-degree angle on this side. If you haven't yet, pause the video, take a look at this, and figure out how you would approach it based on your knowledge of how math is supposed to work. This one actually stumped me for a little while, but I'm going to go through the process of how I got there. So if you've taken a look at it, let's dive into how we get this done. So a few things we need to know to solve this. We need to know where the center of that circle is. And we can find that by determining what the radius is. So we need the radius, but to find the radius, we also need to know where the center is. It's kind of a double-edged sword in a way. And standing in this framed with a wall this way, a wall this way, and a wall here, trying to figure out where to put this circle, I couldn't see past it until I pulled back and looked at the drawing as it stands right here. And then I could see what I couldn't see from the walls. So with this being a 135-degree angle here, the complementary to that is 45 degrees. And that happens when we take this wall and project it through this way. Then the opposite side here, this becomes 45 degrees. And that is a big key, because if we project this wall as well, being that we have a 90-degree angle in this corner, 180 degrees makes a triangle. That means this corner also has to be 45 degrees. Since we have a triangle with two 45-degree angles and a 90, a right angle, 45-degree triangle, that means our side lengths are equal. We can take the 30 1/4 from here and move it right up here. Then we know from a bigger triangle, we can make a right angle here to where the center of our circle will be. Our center of our circle will be somewhere on that line. We have a side length here, which is 30 1/4 plus 24. That gives us 54 1/4. We have a right angle, 45 degrees, 45 degrees. So the next step is determining how long our radius is on this line. The kind of default would be, well, it's half that line. But that's not true, because our circle will continue down over here and end before this side of the triangle meets. So it can't be half this bottom line. In order to find the center of that circle, we actually need to bisect our 45 degrees at the top. By cutting that angle in half, we have now mirrored this smaller triangle with that smaller triangle, which now also has a 45 degree angle. Now that we have this 22.5 degree angle at the top with our bisected 45 degrees, we can figure out what our radius is. And since we have the same half angle on this side and a right angle at the bottom here from the same point, this radius will also be the same. So now we just take our SOHCAHTOA, the math that we all memorized but didn't know what it meant, to solve for this triangle for R. So we have an angle and a side length which is adjacent to the angle, and we're trying to find the opposite, which is our radius. So that means we need to use tangent over hypotenuse. Tangent equals opposite over adjacent. So we have tan of 22.5 equals our radius divided by 54.25. Simplify that is tan 22.5 times 54.25, 54.25. That gives us radius equals 22.47 inches. Rounding to 1/16, that is 22.5 inches. And I can confirm it did work on site. So sometimes you just need to pull back, take a look, and determine where known variables can be without them actually being drawn for you.
So if this was all helpful, give me a follow here, like the video, comment, subscribe. You can also find me on Instagram at ByronBuilds, hammer.com/ByronBuilds, and for everywhere else that I am on the internet, byronbuilds.com.